So pretty much you're the same people I was just talking to, but Philip's here now. So no classes, my classes aren't meeting at all next week. Because I'm not going to be here Monday. And then the school isn't open, or at least there are no classes in the school Wednesday through whatever. So
You should have just said it's because you want to be extra nice.
He's always extra nice.
No classes next week. And I will give a new weekly assignment, and I will, by the end of this weekend, have your old weekly assignments graded and stuff. And we're about 3 weeks, I think, from the next test, so it's still a little ways out. And so I'm going to do 2 examples. I'm going to do 2 examples today for compressors and pumps. And then the next thing I want to do is just an outline of all the topics we've covered so far before we go into the next big chunk of this class, which is the second law of thermodynamics. And actually, I think there's some stuff that a lot of people like more about the second law of thermodynamics when we start talking about entropy and stuff. It starts to get a little more, it starts to feel a little more sciencey, a little more philosophical in some ways, and a little less of just trying to force equations together. So things will change a little bit. But anyways, so I want to, because that's such a different part of the class, I just want to do a thorough, maybe couple day long summary of where we're at. Okay. But first, let's do a couple examples. So the first one is we have a compressor at steady state. And we're going to ignore changes in kinetic energy and potential energy. And at the inlet of this compressor, the pressure is 1 times 10 to the 5. The specific enthalpy is 290 times 10 to the 3rd joules per kilogram. The mass flow rate is just measured at the inlet. It's coming in at the inlet, 0.1 kilograms per second. Well, it's steady state, so that's going to be the thing for everything. And then at the exit, the specific enthalpy is 1023 times 10 to the 3rd joules per kilogram. What? Yes, thank you. And so if we're given that the electric power coming into the compressor is 77 times 10 to the 3rd watts. What's the rate Q dot for the control volume? So
is
what's
like a super lot? Like 77,000 watts?
77,000 watts. Is that a lot?
I'm trying to think. Like a space heater is 1,500 watts, right? So that would be like, this would be like a freaking huge.
Yeah, that's true, I guess. You're right. Yep. Okay, so like always with these problems, start out with the full form. So d dt is equal to q dot minus w dot plus, this is steady state, so we can just change this to m dot. And h at the inlet, we're ignoring the potential and kinetic energy effects. So I'm going to just leave it like that. And then we have minus m dot times he. Steady state also says this goes away. So we have this form that says, we can write it as w dot for the control volume is equal to q dot plus m dot times the quantity h inlet minus h exit. I don't know. And now we're just looking for what we can fill in. Electric power coming in is 77 times 10 to the third watts. So is that a positive or negative W dot? Negative, yep. So negative 77 times 10 to the third is equal to Q dot for the control volume. And now we can just plug the other stuff in. Our M dot is 0.1. And our HI is 290 times 10 to the third. Our HE is 1023 times 10 to the third. And so Q dot for the control volume is negative 3,700 joules per second. Does it make sense that Q dot would be negative for a compressor? You have the electric power coming in, this thing's heating up and, emitting heat to the surroundings. So that's a negative, that's a heat loss to the surroundings. Any questions about that? I want to do one also where we're doing, so if you're doing a pump where the result is a change in pressure of the liquid, the approach is just like this. So the one I want to do is for a pump where you're changing the height of a liquid. So let's say we have liquid water that's lifted a height of 5 meters. At a flow rate of 0.5 kilograms per second. If the system is in steady state, and we're going to be neglecting kinetic energy effects and heat transfer. What's the electric power required? So I'm going to start with the full form. dE dt is equal to Q dot minus W dot plus M dot. Steady state means that I can write these as M dots, and times the quantity HI plus VI squared over 2 plus GZI minus M dot times the quantity HE plus VE squared over 2 plus GZE. We're ignoring kinetic energy effects. There's no change in energy, and there's no heat transfer. And so I can write this as W dot for the control volume is equal to M dot times the quantity. I'll do this as HI minus HE, and then I'll also add that to M dot times the quantity, and I'll pull the G out of this one. So M dot G times the quantity ZI minus ZE. Okay, well, we are assuming that the temperature and pressure are the same at the inlet and the exit. Okay, because you just have a system. So you can think of your system as like this. Here's the pump. It's dropping this liquid off up here. And all of this is our system. Okay, so whatever the pressure and temperature are there, that's also the pressure and temperature here. And so that means that the specific enthalpy isn't going to change. And so we're left with just W dot for the control volume is equal to M dot times G times Z at the inlet minus Z at the exit. M dot is 0.5, so 0.5 times 9.81 times the difference here is -5. And so we get negative 24.525 watts. For a pump, does it make sense that we have a negative power? Yeah, it works just the same as the compressor. That's the electric power coming in to power this thing. Okay, so I think there's 2 more problems in control volumes that I haven't assigned yet, so I'll assign those. And then the next thing I want to do is just start an outline of what we've done in class so far. It might run past the end of class today. But this is an outline of the class so far. Before starting entropy and the second law of thermodynamics. So we first started with, so section 1 was what I call the introduction. I talked about pressure, definitions of pressure. And there were a couple of things that I talked about here. The first one was for a fluid that's continuous and at rest. The pressure at the lower height is equal to the pressure at the greater height plus rho g h. And we talked about two types of pressure measurements. The first one was barometers. That's used for measuring atmospheric pressure. And the second one was manometers. And that's used to measure pressure in a contained gas. And both of these two equations you can derive directly from that pressure equation. And the second big topic here was work. And let's call this work of expansion. So this was the one I brought up right away. And this is something you can always use. There are no restrictions on when this holds. No, don't do that subsection yet. So the definition of work of expansion is that W is equal to the integral from volume 1 to volume 2 of PdV. One thing to keep in mind about this is a lot of times in problems, we're talking about volumes in terms of specific volumes. This is the extensive volume. So don't just directly plug in specific volumes into this stuff. To compute this integral, you need to know pressure as a function of volume, or often we have this where pressure is equal to a constant. And so the two most common ways that this comes up is the problem gives you a constant pressure, or the problem gives you that exponent relationship between pressure and volume, a polytropic process. So the most common example here is PV to some power is equal to a constant. If you see this polytropic process, recognize that you're probably going to end up computing that integral. And one thing to remember is the only other ways that we see work coming into our problems is electric power. That can be in or out of the system, or rotating shafts. The second big topic was the first law of thermodynamics for closed systems. And so this is that the change in energy in your system is equal to Q minus W. And early on, the biggest thing we were dealing with here was the sign convention. So remember, Q is for heat entering the system. And W is positive for work done by the system. And the definition of that change in energy is the sum of the change in internal energy plus the change in kinetic energy plus the change in potential energy. These two terms are often negligible. And the first important subheading here is we talked about some simplifications for this. The first one is steady state. And that says that the change in energy is equal to 0. The other one that we haven't used too much yet, but we're going to start talking about it more, is cycles. And notice that this standard form of the first law of thermo is over a finite time interval. Okay, and so a cycle says it's not steady state, that the value of these properties can change in time. But if you're looking over a certain number of cycles, at the end of every cycle, all of those properties go back to the original value. So when we're talking about this finite form of the first law of thermodynamics, a cycle means the same thing as steady state. So the change in energy is 0. Then this second subcategory for the first law is, and remember, we're only here talking about the first law for closed systems. We're not talking yet about control volumes. But the second section is the differential form of the first law. And that says dE dt is equal to Q dot minus W dot. So the first important thing to think about with the differential first law is, like, what are the indicators that we're talking about the differential form, that we're going to use the differential form, or let's say indicators to use the differential form. The first one is if you're being given energy values in watts or in any energy per time. The second one is seeing any kind of time dependence in the variables. So, you've seen a bunch of problems where it says the heat is coming in at a rate of 20 T, where T is in seconds or something. That is an indicator that you're going to be using the first law differential form. And then the last one is if you have to use the heat transfer equations, because the heat transfer equations are all given in terms of energy per time. With the finite form of the first law, we had both of these two simplifications. For the differential form, there's really only one of those. And that is steady state. And that says that dE dt is equal to 0. Cycles don't really mean anything if you're talking about this instant by instant in the differential form. And then third are the heat transfer equations. And the biggest thing to remember when you're using the heat transfer equations, so remember, you can't trust the signs coming from the heat transfer equations. When going to the first law. So you have to calculate magnitudes, you have to think about the direction of energy flow, and then you have to use that thinking to figure out what the signs are when they go into the first law. Okay, the sign of Q dot. The heat transfer equations, the first one is conduction. And that says Q dot is equal to, the equation says, this is a famous equation, so I'm not going to change it, negative kappa, coefficient of conduction, times A times the temperature dx. So first of all, that negative is always there in the equation, but just ignore it, okay? Because it's not going to help you when you put this into the first law. And then the second thing is, this A is the area perpendicular to the heat flow. And then in all of our problems, this dt dx is just, we're going to be dealing with a linear relationship between temperature and location. So you can just think of this as the change in temperature divided by the thickness that it's traveling through. The second one is radiation. And the most general form of the radiation equation is that Q dot emitted by your system is equal to the emissivity times the Stefan-Boltzmann constant times the surface area of your system times temperature to the fourth. But I can't really write problems using this because it's missing a whole bunch of, it's dealing with all the stuff that's being emitted by the body, but it's not dealing with any of the heat being absorbed by the body. So for the most part, this is not useful to us. Let's say not very useful to us. So maybe something will occur to me someday where I can make a cool problem out of that, but nothing has occurred to me yet. This is just not the form that you're going to see. The one that you will see is that the net heat emitted for a smaller body surrounded by a larger body is emissivity times Stefan-Boltzmann constant times the surface area of the smaller body times the quantity temperature of the body to the fourth minus the temperature of the surroundings to the fourth. So this is the one that you'll potentially see. So this is only when there's a smaller body surrounded by a larger body. Yeah.
I know for conduction, like the mean of energy transfer is particle to particle, but for radiation, what would that?
Yeah, for radiation, there's no, that can happen through materials, through empty space, because that's electromagnetic waves. So that's how all the energy on Earth gets here from the sun.
So it's 100% through. Would that be photons?
I think yeah, I mean, I think any electromagnetic waves, if you're dealing with it in its particle form, is called photons, I think. But that's so far outside of what I know anything about. But yeah, I mean, actually, I do know that you calculate that using the wave equation. And I mean, there's nothing cooler than the wave equation. Like, so how does this work? So from Maxwell's equations, how many of you guys have taken physics 2? Okay. So from Maxwell's equations, people found that it's definitely not obvious. You look at Maxwell's equations, you don't think like this is the wave equation, differential equation. But by substituting them into each other and making some assumptions, I don't remember what they are, the wave equation from differential equations pops out of Maxwell's equations. And the wave equation lets you calculate the wavelength. So if you have something in the differential equation form of the wave equation, you can calculate the wavelength, or it's something that kind of appears in it. So Maxwell and some other people came up with Maxwell's equations. People figured out, I think that was also Maxwell figured out that took the form of the wave equation. From that, they said, oh, electromagnetic waves have a wavelength. Oh no, it wasn't the wavelength that, I think the wavelength does come out of it, but they figured out from the wave equation the speed of the wave. And this is in like the late 1800s. And so they calculate the speed of electromagnetic waves, and they get exactly the measured value of the speed of light. Before that, nobody had any idea that there was a connection between light and electromagnetic waves. But then from that, people are like, these are going to end up being the same thing. And so later, it was proved that it was. But it's such a cool thing, you know? Yeah, no kidding. Yeah.
Thank you for that.
Yeah. And then the last one, it's hard to beat that about radiation, but the last one is convection.
So I make pizza really fast.
Yeah. That's its main contribution to science. Because scientists need pizza. And the rate of heat emitted is equal to, this is the least like law of physics of these. This is just kind of like a curve fit thing, but it's equal to a constant that's just like a fudge factor that you have to come up with experimentally, times the surface area of the body that's being exposed to the fluid, times the temperature of the body minus the temperature of the fluid. And this A, this is the surface area that's exposed to the fluid. So not necessarily the surface area of the entire body. Okay. And remember, I think you did a problem in one of the daily assignments where, or else maybe it was an example I did, but it talked about like a microchip, and it gave you it said one face of this microchip was exposed to the fluid flow, and it gave you a way to calculate the area. So you'd have a different area if you were doing the full surface area, but only one side of it was exposed to the fluid flow.
You meant surface area exposed to fluid, right?
What?
I mean that's
Exposed to the fluid, yeah. Yeah.
Static expressive there.
What?
Static expressive.
Uh-huh. Yeah. Let's see, exposed to fluid.
you said it fluid, you just wrote by it.
I know, yeah. I know, it's trying to think and talk and write at the same time is sometimes a lot for me. Okay, so that is the second big category. And the third big category is material property relationships. And I actually think this is a really good place to stop. So when we get back in a week, we'll start talking about these material property relationships. I think this is kind of the point where the equations you have available can get kind of jumbled in your head. So we'll come back from being away from this stuff a little bit. We'll get into all this stuff in some detail. Try to put it in a kind of an organized fashion, and hopefully that'll help you, get ready for tests and stuff. So that's next time. Anybody have any questions about any of this? So yeah, no classes none of my classes are happening next week. And so I'll see you a week from Monday.